All right, I wanted to start with this warm-up question today about these two molecules. Do you guys think they're the same or different? This drives chemistry students nuts because they look different, right? Let's name them. So if I go to name them, say 1, 2, 3, 4, 5, that's our longest chain. So what would we call this? 3-methylpentane. If we go to name this one, we go 1, 2, 3, 4, 5, and again, this would be 3-methylpentane. So now do we think they're the same molecule? Or they better be if they have the same name. Otherwise, that would get confusing quick. So why are they the same molecule even though they look differently on paper? Yeah, different conformations. We know sigma bonds are head-on interactions. They can rotate, spin around, flop around in space. And that's exactly what we're going to cover today. It's conformational analysis. With conformational analysis, it's basically the assumption that sigma bonds are assumed to rotate. I think I see Anton's notes popping up. I need to fix that. I don't know why it's doing that. It's okay. I'm like, there's some typing going on up there. All right, so conformational analysis, sigma bonds are assumed to rotate. So let's take a look at a really basic example. What would this molecule be called? Ethane. And we can think about this sigma bond in the center as being able to rotate, right? So I made a model of ethane. You guys can too. It's just two sp3 hybridized carbons, and each one of these points indicates some unique hydrogen coming off of it, right? So really, if you think about this, this spins and rotates like a gear. Do you think it has a pretty easy time rotating, a difficult time rotating, or somewhere in between? Pretty easy, right? We said double bonds have a really, really hard time rotating. In fact, you typically don't rotate them unless you excite them with a large amount of energy. But sigma bonds will rotate at room temperature. So this kind of drives people nuts because we use a different strategy for drawing molecules. So let's draw it in the 2D structure. We could say, all right, we've got two carbons. We've got a hydrogen sticking up, hydrogen down here, hydrogen there, another one coming out, and another one going back. However, that assumes we're looking on it sideways, right? What if we decide to look at it going straight down that bond? Then we can actually draw it a little bit differently, and this is called a Newman projection. And with the Newman projection, I oftentimes teach it with this little eyeball, and we look down that carbon-carbon bond just like we're looking straight down to sp3 hybridized atoms. In the front, we represent this with the three substituents. So, whoops, let's do it this way. We've got two hydrogens sticking up. Got a hydrogen sticking down. And then that back carbon, we represent with the circle. And in the back, we have a hydrogen sticking up, hydrogen sticking down, and a hydrogen sticking down. These are the exact same molecule, drawn differently. Has anybody checked out Master Organic Chemistry? It's in the useful links section on the website. If you ever Google a question related to organic chemistry, there's a fair chance his website will pop up. This guy's got a weird sense of humor, and I love it. He has a whole section on everything I learned from chemistry, I learned from cats. So you can see he's got a line wedge cat on the left. He's represented the head with H, his tail with a T, and then all 4 feet using dashes and wedges. You can also draw this using a sawhorse representation, which you guys might have seen in some of your textbooks. That's just kind of a side-on diagonal look at a molecule. And then we've got our Newman projection. So with the kitty cat there, we've got the head and tail sticking up in line. If If you guys want to check out his website, it's a riot. It makes studying organic chemistry a little bit more fun. So let's take a look at ethane again. We said that with ethane we've got this bond line structure, and this time I'm going to color code my bond lines. So just going to fill out my dashes and wedges first. I'll do one that's green, one that's blue, one that's red, and then in the back I'll do a gray, I'll do an orange, either way, yellow, sorry, that's hard to see on the screen, and then we'll do a purple. So let's try to draw this using our Newman projection, and again, I want to imagine looking straight down this bond, but this time we need to color code it. So in the front, we've got two hydrogens sticking up, kind of like arms, right? In the bottom, we have a hydrogen sticking down. What color is the hydrogen that's sticking down? Green. What's the hydrogen in the top right-hand corner? What color would that be? Blue. So if we're looking at it, it's sticking out as a wedge, so it would be over here. And then our red one would be in this position. Conversely, if we look at the carbon behind, we've got three hydrogens. Which one's going to be sticking straight up? Gray. So I'll put in a gray one. What would be down to the left or down to the right? Sorry, let's do down to the right. Purple. And then down to the left? Yellow. So we'll plug these all in. And this becomes important, right? So if we look at the model that I built, there are some situations where they'll be neighbors to one another, and then we can rotate it around, and they could be on opposite sides from one another. So this can freely rotate, but we have to analyze this a little bit. So let's take a look at some conformational changes. And this time I'm just going to focus on two different hydrogens. I'm going to fill in all my spots here. This time I'm going to do one hydrogen in the front as red and one in the back as red. And if we look at these two hydrogens are referred to as anti-periplanar, meaning they're in the same plane as one another, but they're facing on opposite sides. All right, now let's imagine we take this front proton and I'm going to move it. I'm going to twist this whole molecule 60 degrees. And then I'm going to take this proton because it's already locked in and it's going to have to go over 60 degrees. And then same with this one. So this is kind of like going through one of those gates at an amusement park. You guys know those? They've got the three prongs and you walk through it. This is going to take some amount of energy to rotate, but let's do 60-degree turns. So now our back carbon hasn't moved at all, so we'll just draw that in as static. Our front carbon has, and now things are kind of lining up with our other substituents. There we go. Now our red hydrogen's over here, our black one's right here, and our black one's right there. What we do is we try to refer to these using different terminology. So the one on the left is called our staggered conformation. The one on the right would be referred to as what, if it's not staggered? Does anybody know? Anybody read ahead? What do you call two planets when they align?
Eclipse.
An eclipse. So we go from staggered to eclipsed. Which do you think is higher energy?
Eclipse.
Eclipsed one. So if we think about it, these two hydrogens, the ones that are overlapping, each have their own electron cloud. Those electron clouds don't like being close to other electron clouds, so they're not super happy being in line anymore. So eclipsed is most likely going to be our higher energy conformation. And then let's finish turning this a bit more. We'll pull this one down 60 degrees, 60 degrees, 60 degrees. And now our back carbon is still in that same spot. However, our front carbon has changed. And do you think this will be called staggered or eclipsed? Staggered. The way I like to look at this is using something called an energy diagram. And an energy diagram basically tells you how much energy it takes to twist or do a reaction or do something with a molecule. So let me show you guys how I do my reaction coordinate diagram. I've got energy on my y-axis, and I've got rotation on the other axis. So if we think about this, we know that our starting conformation was anti-periplanar. So we've got two hydrogens on opposite sides. And we know that this is staggered, so it's going to be lower in energy. In order to twist it, we're going to have to input some energy. And now this front hydrogen is going to be eclipsed with the back one. So let's label this as staggered and eclipsed. All right, and then we said if we keep on twisting this, we're going to go back down to our more stable staggered configuration. But this time this red proton will be on the far right. Do you think we can keep on twisting this? Yeah, so if we keep on going out, this can continue on forever and ever, until your hand cramps up at least. All right, this does require an input of energy, like I said. This input of energy is 3 kcals per mole. My general rule of thumb is that we've got energy all around us as heat in the room, and that heat energy in the room is roughly equivalent to 20 kcals per mole. So this isn't much of a barrier at room temperature. This is going to spin around like a helicopter blade. It's going to be very, very fast. What do you think will happen if we cool this down close to absolute zero? Yeah, if we cool it down to absolute zero, these would actually be locked and be unable to rotate because they wouldn't have enough energy to even get to that eclipse conformation. They'll be stuck in a staggered conformation. But we know at room temperature we've got more than 0 Kelvin. We've got plenty of energy to overcome that barrier. Does that make sense?
So you're just saying they're going to keep going?
It's just going to keep on going. It's going to spin around really, really quickly. All right, let's take a look at butane. Butane's a little bit more challenging. Temperature is one of the main ones. That's a good question. So the question was, is temperature the only thing that can cause a molecule to spin or rotate? There are other forms of electromagnetic radiation that will also cause bonds to spin faster. However, we're not going to really touch on it in this class.
I think it's lights.
Light, that's a good question. Does light cause bond rotation? Light's a little different. Light has much, much shorter wavelengths. It's higher energy than something like heat. So instead, it usually is involved with exciting electrons up in an orbital, and we'll talk about that when we cover UV vis. So let's do butane, and then I'll ask you guys to help me with all of the conformations of butane. Specifically, I want to look down that 2,3 bond. I've got a hydrogen, I've got a hydrogen, and this time we're going to be looking smack down here. So I want you guys to come up with the first Newman projection, and then do 60-degree rotations and try to come up with as many different Newman projections as possible. So I'll give you guys a few minutes to work on this, but remember, you're going to always go from staggered to eclipsed to a new staggered to a new eclipsed, and then so on until you've done a full 360-degree turn. So I'll give you guys a minute to work on this.
You just draw
That makes sense. Do you always draw the back one that's spinning?
You can pick either carbon to spin. Yeah, that's a good question. You can spin the front one or back one. I'm just going to draw in our backbones here. And you guys are welcome to use model kits too. So we're looking down the internal carbon-carbon bonds, and then we're rotating the front carbon 60 degrees, and then 60 degrees again, kind of like a clock, where one arm's acting as a hand, and then keep the back one static or the front one static. So you only want to move one portion. A lot of students are tempted just to tumble the molecule. We want to actually rotate that sigma bond in between the carbon 2 and carbon 3.
Can you go back up for just 1 second?
Yeah. So again, we want the first carbon, or sorry, the first Newman projection to look a lot like this. And we're looking down it like that. And we want to transpose this into a Newman projection. Does that kind of make sense? And then once you think you've got all 6, give me the thumbs up.
Oh, I can see that.
Yep. So the circle in the Newman projection is representative of the back carbon. The one where it crosses, this is the front carbon, that circle is going to be the carbon behind it. So we indicate that they're different. that way. Does that make sense?
Can you repeat that? The circle behind is the back carbon.
So here, let me use my pen real quick. So this carbon right here is going to be this carbon in red, right? This back blue portion is going to be this carbon in blue. So we represent that back carbon using a circle.
Technically, wouldn't that back carbon in perspective be smaller than the front one?
Yeah, we just don't have a good way of drawing it with perspective in this way. So this is the standard way that's been done since the 1920s. I didn't come up with the rules, sorry guys.
Your name, Lewis.
I'm no Lewis. All right, I'm getting more thumbs up. Raise your thumbs up if you've got at least half. All right, it looks like we've got most of them. So let's start at 1 here, and then we'll rotate them 60 degrees and kind of go clockwise around there. So what should be sticking straight up? CH3, right? That back carbon has a CH3 sticking straight up. What about if we go clockwise? What's the next thing coming off?
It's front hydrogen.
Front hydrogen. What about next clockwise around?
CH3.
Oh, it'd actually be another hydrogen. And then bottom, we've got a CH3. And then we've got a hydrogen and hydrogen. So let's look at this with our model kit again. So I'll go up to the screen. I've got my CH3 up in the back. I've got the CH3 pointing down on the left. All I'm doing is I'm spinning this around. Right? And so now this CH3 in the back sticking straight up, the one in the front sticking straight down. What would we call this conformation, do you think? It's going to be staggered. And then would it be syn or anti-periplanar? What do you guys think? So this is staggered anti-periplanar. All right, so now if you notice, I'm holding my front carbon static. That means that intersection point's staying the same. And I'm just going to spin that back carbon around, right? So if we look at it like this, I'm just going to rotate it 60 degrees now. And we're going to form an eclipsed conformation. So I've got CH3, got H and H. Now we're going to take that CH3 that was sticking up in the back, and it's going to be eclipsed over here. We've got hydrogen and hydrogen. Is this going to be more or less stable? Less, right? So we know that eclipse conformations are going to be a lot less stable. All right, then we're going to twist it another 60 degrees so that now this CH3 group is going to be right here. The front carbon we're going to hold static. All right. Now we're going to try twisting it one more time. If we do that, now we've got two overlapping methyl groups. Got a hydrogen, 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 and hydrogen. Let's keep on twisting it. So this CH3 in the front we know is going to always stay put. But now this methyl group's going to keep on moving by. I've got a hydrogen up top and a hydrogen right there. And then last but not least, we could have this CH3 stay put. And now we've got a CH3 in the back that's eclipsed. If we rotate it 60 degrees more, we're right back where we started. Does that make sense? It's kind of a goofy way of looking at this, but let's finish labeling all of these. We know that this one will be eclipsed. We know this one will be staggered. We know this one will be eclipsed. This one will be staggered. And then this one will be eclipsed. The one that is, let's see, right here, let me highlight it, also has a unique name. If we think about those CH3 groups, they're now in plane. So we would refer to this one as syn periplanar. Anti-periplanar is where those methyl groups are on opposite, or they're pointing out in opposite directions. Syn means they're pointing in that exact same direction. All right, now we've got a tricky thing to do. We've got to assess the stability of all of these different conformations. This takes a fair amount of work. Which one do you think is going to be most stable? Do you think it will be 1, 2, 3, 4, 5, or 6? 1. Why do you think 1 is going to be most stable?
Methyl groups are furthest.
Yeah, the methyl groups are furthest away in 1, and we know that molecules that have big electron clouds want those electron clouds to be far apart from one another. So this will be our most stable. All right, what would be our next most stable?
3, 5, no.
Ah. So you said, I heard somebody say 3 and 5. Is there really a difference between 3 and 5 in terms of stability? No. So we would say these would be second. Most stable, it's a tie for second. And then what do you think about third most stable?
2 and 6.
2 and 6. So both 2 and 6 are eclipsed where we've got a methyl group overlapping with a hydrogen in 2 spots. So I agree. This would be third. And this one would also be third. And that leaves, last but not least, this one as least stable. Which makes sense because if we think about those methyl groups as being their own little helicopter blades, you don't want 2 helicopter blades getting close to one another. That's a lot of electronic repulsion. So again, what we do is we try to turn this into a reaction coordinate diagram or an energy diagram. And I'll show you guys how we're going to do this. Looks a lot like this. Some people say it looks like a middle finger. And then we'll try to fill this in. Got CH3, H. We know this one's going to be our anti-periplanar. And then if we rotate it, this time I'm just going to rotate the back one. That we're going to jump up in energy. This jump in energy to this conformation that is now eclipsed is about 3.6 kcals per mole.
I think you missed a CH3 on that second one.
Oh, I did. Thank you. It should be down here. Good catch. So, will this occur at room temperature? Yeah, definitely. And then if we look at this next one, we're going back down in energy. Because we're going back to an eclipse conformation. And now this CH3 will be over here. And then if we go up to that really unhappy conformation, that syn periplanar position, now we've got the 2 methyl groups running into one another. And then we can keep on rotating it back out. So let me do this arrow. And then the last two are the other ones we had drawn. So I'll go CH3, H, H. We're going back to our eclipse conformation, and then last but not least, we go right back to our same starting material. You guys are going to get good at drawing in this class.
I just numbered one.
You just numbered yours?
Yep.
Yeah, I guess that's fair. All right, so let's take a look at some of these other energetic barriers. In order to go to this Antiperry planar conformation, it takes about 6.0 kcals per mole. Oh. And if you're just looking to make this transition from one staggered conformation to the other, you can do the math, and this is only about 0.9 kcals per mole. Oftentimes people will ask me, why are we using kcals instead of kilojoules? In physics, I was always taught to use scientific notation. The honest truth is chemists are stubborn and prefer kcals per mole. You can use kilojoules per mole. It's been ingrained in chemistry for so long, it's been hard for a lot of people to switch to SI units. All right, so let's go back up, and I want to take a look at these conformations one more time. And I wanted to introduce some new terminology. And this terminology is used to describe destabilizing interactions. Specifically, this interaction between this methyl group. So the methyl group in the front and the methyl group in the back. This is referred to as a gauche interaction. If we go over to this position, we've got another gauche interaction where those two methyl groups can feel one another in space. What about in our staggered antiperry planar one? That first one we drew. Is there any gauche interaction? No, they're too far away. So gauche interaction is only felt when you've got alkyl groups in the front and back that feel one another, meaning they're within 60 degrees. So this staggered gauche conformation is destabilizing compared to the staggered antiperry planar conformation. So I'll refer to this a lot throughout the year. I'll be referring to steric interactions or gauche interactions when we're talking about Newman projections. A steric interaction's synonymous with the gauche interaction. It's just two big bulky groups kind of brushing up against one another. Does that make sense? All right, I've got a challenge problem for you guys now, because you guys like those. Oh, this one's related to your pod. So this one says, draw all three staggered conformations for the following. All right, and however, this time we're going to be looking smack down this bond. So we're going to be looking down the 3,4 bond in this molecule. This would be 3-methylhexane. So let's try to figure out our three staggered conformations for this molecule. And then give me a thumbs up if you think you got all 3 staggered conformations. So you don't need to do eclipse, just staggered. So only 3. I'm going to make these worth 3 points each. So there we go, 3. Oh, I'm running out of room. 3. I'll do something that'll make your life a little bit easier too. Carbon 5 and 6 and 1 and 2 are what sort of groups? Ethyl. So we will abbreviate these as ET and ET. Sorry, that might have made things go a little faster to begin with. I also personally guarantee that there will be a question just like this on the exam. So let's do our first box. Just the conformation I have drawn, right? What should be sticking straight up? An ethyl group, right? So if we're that blue eyeball and we're looking down that 3,4 bond, that ethyl group is sticking straight up, right? What should be to the bottom right? The CH3, right? If we're looking down the 3,4 bond, the CH3 would be going to our right. So we need to label this as CH3. That means that that assumed hydrogen would be going to our left. All right, back carbon now. We'll draw our circle. We've got 3 substituents. What's going up to the top right? Hydrogen. What's going down? An ethyl group now, right? It's in the same plane as that other ethyl group, which makes sense. And then last but not least, we've got this other hydrogen. All right, this time what I'm going to do is I'm going to keep the front carbon as is. This will save a little bit of time, and we'll plug these in. All right, so front carbon static, and we're going to twist that back carbon, and we're going to go clockwise 120 degrees now. So we're going to take this ethyl group, spin it over here, this hydrogen, spin it over here, and this hydrogen will replace where that ethyl group was. All right, that means what will be pointed down now? Hydrogen. And the ethyl group will be to the top right or left? Left. That means our other hydrogen will be here. And then last but not least, we can keep on twisting this, and we could say, all right, this ethyl group is now going to go where that hydrogen is. This hydrogen is going to go where that hydrogen is, and this hydrogen will go where that ethyl group was. Oh. All right, now the tricky part. Which one's going to be most stable, second most stable, and least stable, and why do you believe that? Try to convince your neighbor.
Oh, actually, that one is going to be the least stable because the ethyl's oh, that those are close to the so least energetic. Energetically
All right, let's come back together and look at these. How many people think A is the most stable? All right, let's look at this. Does A have any Gauss interactions?
Yes.
Ah, it does, right? We've got an ethyl-methyl Gauss interaction right there. What about that ethyl on the top? Does that have any Gauss?
No.
No. All right, now let's move on to B. Does B have any Gauss interactions? Yep, we've got an ethyl-ethyl right here. What do you think's worse, a methyl-ethyl or an ethyl-ethyl? Ethyl-ethyl. And then C, do we have any Gauss interactions? Two Gauss. This is not good. So if we were to rank these, we would say most stable. Would B be second most? I'd say so. I'd say second most. Oh. And then least stable. Make sense? Sometimes it takes a little bit of practice. If you're three-dimensionally challenged like I am on occasion, a model kit comes in handy. On quizzes and exams, you can come with models pre-made, so you can come with a butane or some other chunks and just attach them together. I'm perfectly fine with that. So use study tools if you're struggling with this. All right, there's a harder Newman projection to draw, so let's go to that.
I have a question about cis and anti-Perry planar.
Yeah.
If they're all, like if it was an ethane and all the hydrogens, they're all hydrogens, would every staggered be anti and every eclipse be?
That's a good question. So with ethane, the question was, would everything be anti-Perry planar? Yes and no. Typically, when you're referring to syn or anti, you're comparing two substituents, usually identical substituents. So if we go back up and we look at the case with our Newman projection here, we said staggered anti-Perry planar. We were comparing those two methyl groups in the front and back, where syn eclipsed means that they're going to be overlapping. Yeah. All right, let's go on to one more thing. This will help us tomorrow. This is our conformational analysis of cyclohexane. There are three common ways to draw a cyclohexane. All right, the first one is using bond line. So what do you guys think that looks like? Hexagon. Pretty simple. Next one's a Newman. All right, with the Newman projection, what we're going to do is we're going to have two sets of eyeballs. We're going to look down parallel bonds. So let's imagine this as being two Newman projections that are attached. You'll notice that the carbon in the front I have puckered down.
You need a down.
So that's a CH2 linker in between. So I'll write CH2 is puckered down. This CH2 is puckered up in the back. Does that make sense? Why do I have to show it as being puckered up and down? Yeah, because they're sp3 hybridized. If we look at the bond line structure, it's really tempting to say all of these atoms are flat. However, we know according to Vesper rules that they're not going to be planar. We have to have tetrahedrons on every single carbon. If we look at it with this, sorry, I forgot this guy, that hydrogen. If we look at each of the carbons here, now they're all tetrahedral and they're happy, right? I will say that not a lot of people draw the Newman projection with cyclohexanes because it takes a lot of work and it can be quite sloppy. So instead, what people often do is they draw what's called a chair, or some variant of a chair. With the chair conformation, you have two parallel lines. And we'll practice drawing this, trust me. And then we've got a carbon in the front, carbon pointed down. Don't worry if this is going super fast. We'll practice it a lot tomorrow. You guys all keep up? Let me actually make this a little bit smaller in the back. There we go. All right, so this is our chair. These are all the exact same molecule. And I want to show it using this video. See if it works. We've got 2D, Newman, chair. Then 2D, Newman, and chair. So really it's the same molecule, just viewed 3 different ways. A lot of people really struggle with this. But what I want you guys to do is if you have a model kit, prepare cyclohexane for tomorrow. We'll practice drawing cyclohexane, and then we'll do the same thing we did today. We'll do some conformational analysis, we'll spin some sigma bonds, and we'll assess what happens to cyclohexane every time we twist it or spin it or rotate a sigma bond. All right, I think that's where we're going to end today. If you have Thursday lab, remember you're welcome to come to lab today to get things done early.